Okay, explaining thermal expansion with these potential energy well curves, that's pretty slick. What else can they tell us? Well, what about stiffness? Can they tell us about stiffness? Sure. If we think about it again, let's draw it. Now, this time I'm going to draw the force curve. It's a little bit easier to see on the force curve, so I'm going to draw force here versus interatomic separation. So here is R. This time it's force F. Right there, that is R naught. Right, that's the point, the bond distance. Okay, and we remember what our curve looks like. It went up like this, and then kind of down like that. So, what is the stiffness of a material? You know what stiffness is. It's if I take a material, I can bend it, right? I can bend this material if it's compliant. If it's an easy to bend material, we call it compliant or low stiffness. Whereas other materials are much harder. Like this wood's going to be much more stiff than that hollow pen that I had. It's more stiff. So it takes a greater force for me to bend this thing to get deflection, to move the atoms. It takes a greater force for this than for the other material. So what does that look like here? Here we've got force, and we're trying to separate things, right? So in order to separate something, say from where it wants to be, which is right there is R naught. Let's say we want to bring it out to here. That's R1, some distance away from its initial spot. What do I have to apply? I have to apply a force, right? So the force that I have to apply is going to be equal to, it's going to be the tangent of this line there, right? So if I drew this tangent line there, the slope of that line, that's the force that I have to apply when it's at rest to get it to start to move. Does that make sense? So the slope of this, that is going to be proportional to our stiffness, right? So the stiffness, which we call E sub y, that stands for Young's modulus. Young was an amazing guy. He was like an Egyptologist among many other things. He also did material science and mechanics. So Young's modulus, named after him, it's going to be, I'm not going to use the equal sign, I'm going to use the proportional sign. This little alpha symbol, that means proportional, meaning that there's a fudge factor in front of it, but it scales like this. 1 divided by R naught, right, whatever your interatomic bond distance is, multiplied by the slope, right, we want the slope of that point, so that's going to be df dr. We're going to take the derivative of the force expression with respect to R, evaluated at R equals R naught. So at this point, we want the slope right at that tangent point. I haven't drawn it really great here, right? But it's at that point, okay? That will give you the stiffness. So if you have different materials, let's say you've got a different material that might have this as a curve. Maybe this is a polymer material. Well, from practice, you know that polymers are less stiff than metals. You can bend them more easily, right? So what's actually happening here is it's just less steep at that point on the curve, right? Right there, it's less steep at that cotangent point. So it has a lower Young's modulus. So all of a sudden, we can use this to get lots of interesting information. We've already gotten thermal expansion, we've gotten stiffness, we already talked about melting point. So you can get a lot of interesting information by understanding these potential energy wells.